Let me also use this opportunity to say Alexander Sergeyevich, с наступающим днем рождения. And for the talk, I apologize for those who have already heard this one, a similar talk. Well, I will start by some introduction, and then I will give a list of recent examples of varieties which are proved to be not stably rational and even not retract rational. So these results were obtained by the method using the specialization properties and Chow group of zero cycles. So I will explain this method, and I hope this will be the main part of the talk, and it will be actually on the blackboard. And we will discuss more in details one example, namely quartic threefolds. So let me start by introduction. Well, if you take a field and an integral variety of a field, then you may be interested to know if X is rational or if X is stably rational. Just to recall, this means that a product of X with some projective space is rational. Obviously, one property implies the second one. Or also if X is retract rational. So let's recall the definition by the factorization property. So you want to have an open in X, and there is open as well in some projective space of some dimension, and two maps from U to V and from V to U, such that the composition is identity on U. So the identity factorizes rationally through a projective space. Well, and all these properties imply that X is unirational. So you may notice that some of these implications are red ones, and there is one black one. So the red one implications are strict, and it's still an open question to know if the black implication is strict as well. And also all these properties are birational properties, so if you prefer, you can define them just by looking at the function field of the variety X. So let me give examples showing that the red implications are strict. So it will be over the field of complex numbers. First, so there is a threefold which is stably rational but not rational. So it turns out to be actually a conic bundle, and such an example was produced in the common work of Bouville, Colliot-Thélène, Sansuc, and Sunyater d'ailleurs. Then, also there are examples of varieties which are unirational but not rational. Well, it was an open question till 70s, and then three examples appeared. So let me just use a notation for now and for the rest of the talk. By XD, I will denote a hypersurface of degree D in projective space. Okay, so any smooth cubic of dimension 3 is unirational, but no one is rational. So this was done by Clemens and Griffiths, who used the intermediate Jacobian criterion. Next, if you look at quartics, also smooth quartic are never rational. This was done by Iskovsky and Manin, who used the rigidity properties of automorphisms of X. And some of such varieties are known to be unirational, but it is still not known if all of them are unirational, and seems to be quite a hard question. Well, and the third example is a series of some particular varieties constructed by Artin and Mumford. So these are double covers of P3 ramified along a quartic with some particular choice of coefficients of the quartic. Let me just make tell you three properties of this. So this still could be defined over Q bar. And this variety is singular. It has 10 ordinary double point singularities. I will also call them nodes in what follows. So the important property is that if you take any resolution, so any smooth and projective variety which is birational to Y, then it turns out that there is a non-trivial torsion in the third beta cohomology of Z, which turns out in this case to be equal to the Brauer group, and which is non-trivial. And this forces Z to be not retract rational. Okay. So now if you are interested in stable or retract rationalities of these two series of varieties, so you see that actually the invariants used to show that they are not rational do not allow to understand whether they are stably rational or not. So let me now give a list of examples of varieties which are not stably rational, and then go to the method. Claire Voisin studied this series of examples. She was interested in double covers as well of P3, ramified along a quartic, and this time with at most 7 nodes. So she proved that a very general such variety is not stably rational, not even retract rational. And very general here means that you want to remove a countable number of conditions on coefficients of these varieties. So you remove a countable number of closed conditions. And also, so in the case of double covers with precisely 7 nodes, previously it was not even known if such a variety was rational or not. So this result is stronger in this sense. Next, in a common work with Colliot-Thélène, we showed that for quartic threefolds, a very general one, also is not retract rational. And one can tell more. For instance, there are examples over Q bar. And also after the work of Totaro, you can also produce examples over Q bar. Over Q. Next, Bouville was interested in double covers as well, so of P4 or P5 branched along a quartic again, or of P3 branched along a sextic. Very general, is not stably rational as well. So Totaro proved that much more hypersurfaces not retract rational. So a very general one with these assumptions on the degree. So in particular, if you take n equals to 3, so for threefolds, then you can make the exercise to see that the quartics are again in this list. Also, many conic bundles over rational surfaces, so this time over a field which is algebraically closed, not necessarily of characteristic 0, but just characteristic different from 2, are not retract rational. In particular, so I'm not giving the precise statement, but in particular, you can take a very general conic bundle over P2, and you need the discriminant curve to be reduced, and here you have to take the degree at least 6. So this works. So it was done by Hasid, Crash, and Chenko. And finally, we were again interested in cyclic covers, this time of prime degree P, and ramified along a hypersurface of some degree, which is divisible by P. And with these conditions on the degree, you can also get that a very general one is not retract rational.
Cyclic cover of what?
Of Pn, sorry. Yeah, of Pn, thank you. Okay, so before explaining the method, let me discuss the case of, yes?
On that first slide, when you can turn one of your black arrows red because you're over a general field. They're retract rational field.
Yeah, yeah, thank you. Yeah, for over C, of course, it's open. Yeah, over C. Yeah, thank you. But I meant over C. Thank you for correction. Okay, so. Well, for classifying spaces, consider an algebraic group over a field K. And now I will be more precise about the field. You may be interested in this kind of questions like stable rationality for the classifying space of J. So the way to do it is to consider, as we saw in previous talks today, is to consider some particular G-torsor, which is obtained in this way when you take an open in some G-covariance subset, in some generically free representation, the J, and then you produce a G-torsor like this, and then you say that Bj is stably rational or respectively retract rational if this quotient is. So in this way, you think about the quotient as a variety which approximates Bj. And this definition does not depend on the choice of such U and V, And so it makes a correct definition for Bj. So here's an open question, is if you take a connected algebraic group of an algebraically closed field, is there a Bj which is not retract rational? And so indeed, these two assumptions are important, because there are such examples with J finite by Saltman and for is K not algebraically closed by Merkuriev. Okay, so this is for classifying spaces. Now let's go back to hypersurfaces and see what can we do. I will give a very brief description of the method, and then we will see it more in details. So it contains 3 steps. So first, I wanted to say that for this kind of varieties, like hypersurfaces, double covers, well, if you want to understand whether such a variety is stably rational or not, so what you can do, as usual, is to find some stable invariants which are supposed to be trivial for like stable rational varieties, and then compute for your variety, and then maybe find something non-trivial. So among these stable invariants, there are like unramified cohomology groups, Grau groups, things like this. But it turns out that often they give nothing about such kind of varieties, so they are trivial, or maybe we cannot understand them. So this is why to get around this problem, so we use the specialization properties. So try to specialize your variety to something, and find invariants which are suitable to this. So then you want to specialize to something which I call bad, meaning that it has a non-trivial invariance. And finally, so you have your proper definition of interest and varieties, and then probably you want to specialize your interest and varieties to these varieties with non-trivial invariance. Okay? So now I will explain this in more details, and let me just tell that for cubics, as usual, the question is still open. Okay. So now, may I have the yes, close the projector, and I will go to the blackboard. Okay. Okay, so let's consider invariants. Well, to start with, just fix K field and take a proper variety X over K. So because X is proper, you have for Chow group on X of cycles of degree 0 of 0 cycles, then you have a degree map, because X is proper. Now, usually the kernel of this map could be huge, but the situation of our interest will be the one where it is actually very small. So I will say that X is universally CH0 trivial. So if this map is an isomorphism, but universally, so if I extend these colors to some field extension, it will stay isomorphism. So for any field extension. And here any really means any, so not necessarily algebraic, or so really any field extension. So at this point, I usually ask if somebody could give me some examples of such varieties. PN, okay, thank you. So it's my statistics is 100% PN. And then, oh, that's the first one. So, well, maybe I should wait more, like to break down my statistical analysis. Generalized cross-median, okay, very good.
Any so
Any? Cellular variety also, okay, understood. People here are very interested in cellular varieties, things like this. Well, according to the definitions I gave before, any stably rational variety actually satisfies this property, and any retract variety as well. So it's a good exercise to understand which properties the rationally connected variety satisfies. Satisfy this property over C. Yeah. But if I take an extension, then it is not true anymore. It could be false.
If it's false, they have an example of a rational connected variety that's not non-rational?
No. It's just that they are equivalence over the extension is not necessarily trivial, even if it's trivial over C. Okay? You have many rational curves, but over C, not if you extend these colors. So. No, not necessarily. I mean, it's unclear. Okay, so, okay, retract rational. Okay, so now let's consider the relative property. So if I take a proper map of varieties over K, proper map over K, then again I can consider their push forward on cycles between the Chow group on X and on Y, and we say that this map is a universally CH0 trivial. If this map is an isomorphism universally, so again for any field extension. Okay. So now maybe if you want to relate this property to the previous one and to know how to check this universal CH0 triviality for a map. And so the first proposition tells you that actually if you know that your fibers are trivial, then the whole space is trivial in the following sense, that if in this definition for any point M, and here M really means any, means scheme point, not necessarily closed point. And actually the important points here are function fields of curves. The fiber xm, which we view as a variety over the residue field of M, is universally CH0 trivial. Then the map is, sorry, I said total space, I meant map, is universally CH0 trivial. Okay. So this proposition will be useful for us because we will be interested in the situation when this map is a resolution of singularities. And understanding its fibers means understanding the exceptional divisors. And in our case, the exceptional divisors will be quite easy, meaning that there will be rational varieties or unions of rational varieties, so it will be reasonable to apply this proposition. Okay. So these properties of universal CH0 triviality were also considered in works of Merkurjev and also in works of Totaro. And let me first discuss the consequences of these properties and then how to put them into a specialization situation. Okay. Yes? Not necessarily. I mean, I never said in the... Well, very soon we will pass to k equals to c. But a priori, well, no, it could work just like this. Okay. Well, so what can we do? So we take a variety which is universally CH0 trivial. Well, then, because of this property, you have a zero cycle of degree 1. And then also, by the way, we're allowed to produce, to take some field extension. So at this point, I usually ask the second question to choose your favorite field extension.
Join T.
Join T, okay. First time I had this. Okay, next.
No, join KFX.
Join QFX, yeah, first, thank you. So, yeah, you join, you go to the functional field of X. And here you have also an interesting zero cycle of degree 1. It's just the generic point of X, okay? So, generic point. Well, and now we know that the difference, it's a zero cycle of degree 0, so which is trivial on XL. Okay? And also, if you spread out this quantity, then you have the following. So if you consider the Chow group of dimension of X, X cross X, then you can write the generic point corresponds to the diagonal, and then the little x corresponds to this cycle. And then the fact that it's 0 when you go to the generic point tells you something for the difference, so z, where z is supported on d cross x with d of codimension at least 1. So I can write codimension 1. Okay. So if it holds, we will say that, so let me call this decomposition star. And we will say that X has integral Chow decomposition of the diagonal. Of diagonal. Well, these kind of decompositions, it was already considered by Bloch and Srinivas, for instance, but with a multiple here. And here it's important that really we consider the integral decomposition. It turns out that actually for smooth varieties, the zero cycle we choose is the only one to check. Okay. So X smooth, then, well, smooth meaning that, means smooth and proper over K. Then X is universally CH0 trivial. If and only if there is a decomposition, star. Okay. Well. And this is actually very important for to get the following consequences. Could you read from here if I write here? Yeah. Okay. So, okay, now the properties of CH0 trivial varieties. So consider again a variety over K, so smooth, and so say proper projective. Universally CH0 trivial. Then, let me start with the case K equals to C, just by psychological reasons probably, because the second case will be a more general one. So in the case of complex numbers, so the Artin-Mumford invariant of X is trivial. And also, if you prefer Brown group, it's also trivial. And if you prefer the high-dimensional cohomology, unramified cohomology groups, they are also trivial. Sorry, maybe I'll write it here. And HI unramified with some torsion coefficients, also trivial. for at least 1. And all these properties could be generalized as it was done by Merkurjev. So you consider more generally any cycle module over the field. So if M is a cycle module, so in particular the unramified cohomology, you obtain them in this way, is a cycle module over K. Then you cannot have non-trivial unramified elements universally corresponding to these cycle modules. Then for any extension L over K, extension, so the cycle module is a functor on the fields by definition, so you can evaluate it on L, and also you can evaluate it on the function field of X over L, and there are residues here, so you can define also the non-ramified elements, and then you have here a natural map, and it's an isomorphism. So you have nothing on non-trivial here, only elements coming from the base field. Okay. Now let me explain the specialization properties of the universal C0 triviality. Okay, so specialization properties. Well, first we will consider a local context. So in a local context, you want to take a discrete valuation ring. So let me call it A, discrete valuation ring. Then you consider its residue field and then the field of fractions, and then consider X over A, which will be proper and flat. No more assumptions, in particular, no assumptions on the regularity of this whole space. Okay? Let me call the special fiber Y and the generic fiber by X. So the key point here is that in this situation you have a specialization homomorphism between the Chow groups of X and it goes to the Chow group of Y. So here this map is relatively easy to construct because Y is just defined as a principal divisor on the total space, and in particular you don't need to read the whole book of Fulton but just 20 first pages. And then you know that how to construct this. Okay. Well, okay. Now let me explain the proposition. So assume, so it will be proposition 4. Assume first that X, so X is a generic fiber, okay? So X is smooth and universally CH0 tree. And this is actually the smoothness hypothesis is not necessary. So alternatively, you can assume that exists a resolution of singularities, a resolution such that the resolution is the universally CH0 tree. Okay. So no problem with smoothness here. And also the second assumption is to assume that exists so Y is integral. Sorry, Y is integral. So, and exists a resolution F. So Z is smooth, birational to Y, proper, such that the map is universally CH0 trivial. So this is very important. So, and also assume that that Z has a zero cycle of degree 1. So then you have a specialization of this property. So the fact that it holds for X means that it holds for Z. Okay, so the conclusion. So then Z is universally CRT rational. Okay. Well, I will also give an alternative version, which is a more geometric statement. Sorry? So you can look at the diagram just on the upper board. They are generic and special fiber of some space. Okay, so X degenerates into Y, and then you want to use to see how this property specializes. So let me call it for prime. So in the condition I, you just change it by I prime, saying that over an algebraic closure of the field of fraction, you have a universally CR0 trivial variety. Okay, or alternatively, for X tilde of an algebraic closure, you get for the second one, you just add that the field is algebraically closed. The residue field is algebraically closed. So then the condition of having a zero cycle of degree 1 is not really necessary, and then you have the same conclusion. Okay. Well, this is for local specialization proposition, and let me give a global one. Let me formulate it over a field of a characteristic 0, algebraically closed. But you can also take a field of positive characteristic, but it's, well, for our purposes, it's enough. Well, consider a global family. So a global family will be a family X to B, just a map, which is dominant and projective. So this global statement will be for the property of the decomposition of the diagonal. So assume that you have a point in B, okay, such that the fiber at this point has no decomposition of diagonal. So I still keep it like this, just for short, okay? Has no decomposition there, okay? Then the same property holds for a very general point. Then for B in B of K, very general. The same conclusion for the fiber at B, no conditions. So I mean, if for finite type of K integral, say, could be singular, whatever you want. Yeah. If you want integral, just to speak about a family, be of finite type. On smoothness, no. Well, no, actually, well, I didn't want to discuss this. You want the diagonal of the map to exist as a cycle. So you don't want some emerged components, so very, very weird things. But in the case we will apply, this holds. Okay? So not very weird, the correct And of course, flat works. Yeah, that's flat certainly works. Well, now I guess that I have time to explain the proof of the proposition 4, just to explain what is behind, and to work with the definition. Okay, so proof of proposition 4. So because we have a discrete relation ring, so the proposition is here, okay? Have a discrete relation ring, so it's often useful in the beginning to assume that the ring is Hansidian. So let's do this. So first, the case A Hansidian. Okay, then we have a lemma, which is proved just in one line. So if you consider a cycle, a zero cycle on Y, so this is a notation for the group of zero cycles. And I suppose that it's supported on a smooth locus of Y. Supported on Y smooth. Then the image of this zero cycle is 0 in the Chow group of Y. Okay. So the proof. So here is why we assume that A is Hansidian, because you have X and Y are the same as in proposition 4. I wrote proof of proposition 4. Okay, so okay, because A is Hansidian, then you can lift your zero cycle Xi to X because it's supported on a smooth locus. Okay, A Hansidian, Xi lifts to Xi1. Zero cycle of degree 0, yes. Yes, zero cycle of degree 0, thank you. Of course. Okay. And now we have, as I recalled before, so we have a specialization map from X to Y, which is constructed precisely in such a way that the lift Xi1 goes to Xi. But this one is 0 by assumption. So like this, you see that actually just knowing that the Chow group of X itself is trivial is enough. Is trivial as you see. And so this implies that Xi equals to 0. Okay. Well, this is for the lemma. And now let me explain the proof of the proposition. And actually, I wanted to do it just to show that the assumption on F is actually important. Okay. Oh, wait, no, okay. Yes. No, it's a resolution. So sorry, I mean that Z is smooth and birational. Yeah, you're right. Yeah, you're right. Yeah. Well, the way I will prove it, okay? The way I will prove it, it will be for Z smooth. But I guess that you can argue differently, slightly differently, to prove something more general. But now I will give a proof because it's a short one, just for Z. So indeed, the first thing I wanted to say. So general case. Well, because Z is smooth, then we saw that what we actually want to prove is that enough. So enough to prove that the generic point minus x is trivial in the Chow group of z over the function field of z, which is the same as the function field of y because it's birational. Here x is a zero cycle of degree 1. And because we have a moving lemma for zero cycles, we can may assume that x is also actually in the open, which is f minus 1 of y smooth. Okay. Now somehow you want to produce a situation with Henselian discrete relation ring, which takes care of this zero cycle. So to do this, you consider the following discrete relation ring. So let me put B, the local ring of the whole space at eta. Well, probably I had to assume that y is geometrically integral. Well, well, anyway, it's a discrete relation ring. This case, and then I take the completion. Eta is a generic point of z. Also, I can view it as a generic point of y as a point of my whole space. Okay. So, well, let's see what is the picture. So we have B. The residue field is k of y. The field of fraction, I will call it f. It's just a definition. Then we have here the space which I extend to B. I have y over its function field, and also f, and also z, the one I'm interested in, and also here I have just x over, over f. Now here I have my zero cycle eta minus x, which goes to some cycle xi on y. And because of the lemma, now we are over Henselian discrete relation ring. And the assumption was that the generic fiber has trivial CH0. So this one is still universally CH0 trivial. And so it tells you that by lemma, xi equals to 0. And now we see that the assumption of f on f is important because we know that the image of this cycle is trivial. And so this implies, because of the f is universally CH0 trivial, that the difference eta minus x is trivial, and so it is what we wanted. Okay. So now if you do not like manipulations with cycles on the blackboard, and if you use this moment to sleep, then I can suggest you to wake up and to listen how to apply these things to quartics. Okay. Sorry? Yeah, I mean, here, yes, yeah. Well, what will I do? Probably... Okay, well, in this way, we accomplished the first step, meaning that we discussed the invariance we will use. Now we have two things to do, is to construct a family and to find some bad members of this family. So constructing a family in this case is quite easy. So, okay. So the family of quartics is straightforward. You just take as for B the projective space which parameterizes coefficients, right? You have finitely number some projective space of some dimension. One can compute what is this, parameterize coefficients of the quartics and P4. And then you produce the corresponding family X over B, family of quartics. Okay. Well, now let's produce a bad quartic. So recall that we have a variety of Artin-Montfort, which is a double cover defined like this. So here you have a square, and then you have a polynomial which is homogeneous and of degree 4. So this looks pretty much as a quartic, but it is not. So there is one problem here, just one coefficient. So usually I ask also here the third question, so what will you do to produce a quartic here? Cheat. How? This is too complicated, this parameter t. Yeah, so Mark, thank you very much. So so the most maybe easiest solution is to just take some square here, and let me call it y. Now it's indeed a quartic. And the good thing about taking just a 0 is that y is birational to Artin-Montfort. Because you just check at taking z0 equals to 1, and then you have no difference between this variety and the variety of Artin-Montfort. But unfortunately, it's singular. But by doing blowing-ups, you can construct a resolution. So it's proposition 6, I guess. So there exists a resolution z to y, which is a resolution. Dimension is 3 here. So resolution which is f, which is universally C0 trivial map. Universally C0 trivial map. So this is done just by blowing ups, not one, but several times. Well, you see that the variety is smooth, and then you apply the first proposition on fibers to show that the map is universally C0 trivial, because you understand the exceptional divisors. Well, and now the consequence is that you have here a non-trivial torsion, because Z is birational to Artin-Montfort and smooth. So for the non-trivial invariance, we have nothing to do, just use Artin-Montfort. And in particular, it implies that D is not universally C0 trivial. This is probably by proposition, what, 3? Yeah. Because if it's where, it will force this invariant to be 0. Okay? Well, now let's consider how to put these things into the specialization context of the two specialization propositions. Let me just call M in B point corresponding to Y. So Y is a quartic, so it gives you a point. Okay. So let's discuss examples of quartics of X4 in P4 smooth, not, so C, smooth, not universally CH0 trivial. So as a consequence, not stably rational, not even retract rational. So how to produce such examples? So let's produce one and even more. So one example. So the way to do it is to consider your parameter space, which I call B. So we have a point M corresponding to the bed quartic Y, which is actually defined over Q bar, because the Artin-Mumford variety is defined over Q bar. Then you can consider a line through M, line, which is also defined over Q bar. And I can take it in such a way, the generic point. So here, sorry, I have several times the notation eta, but I hope it's clear from the context. What does this mean? So that the quartic is smooth. Just take a line which is not entirely contained in the locus of singular quartics. Then, so we can apply the proposition for prime. Why? Because I can take as a ring R the ring, local ring of L at int eta. So we know that this variety is a generic fiber, and then the special fiber will be Y with this resolution, which is universally CH0 trivial map. And we know that this variety is not universally CH0 trivial. So this proposition implies that X at bar is not universally CH0 trivial. You can still read, remember that for prime was for algebraic closure for X, if you compare it with proposition 4. So let me say how to get even more. So even more. So if you take a point B over, which is a point on a line, but which is not defined over Q bar, then such a point defines an embedding of the generic point of the line to C, identifying somehow the fiber at B to the geometric generic fiber. So via this embedding, you get that XB is not universally CH0 trivial. Okay. Mm-hmm. Well, what should we do to get a very general quartic? So to get a very general quartic, we can apply the global specialization proposition. Okay. So still examples of quartics. So a very general. So now what we got is that we have a XB, a fiber which is so smooth and not universally CH0 trivial. Because it's smooth, this means that no decomposition of the diagonal. And now you apply the proposition 5, which tells you a very general member, a very general XB has no decomposition of diagonal. Because a very general will be smooth, then you have a not universally CH0 trivial. You can also do a different argument here, also using Y, but it's a little bit more subtle. So also I promised examples over Q-bar, so it will be the last example we'll discuss. So how will you get an example over Q-bar? So over Q-bar, so what will you do is that you say, okay, I have what was important here is to construct this z to y, where y was defined over Q-bar. So this map is defined over some finite extension, so let's spread out it over some spec of ring of integers. So there exists an open in some ring of integers of number field, and a map from z to y, so it's not curvy, to y to u, so which extends the map on the geometric generic fiber, such that for any point of u, you have that first the fibers here for the map, so have same types of fibers as for the generic point, and in particular is a universally CF0 trivial map. And also, you may assume that there is, so this time you want some cohomological invariance, so you take a type cohomology, and so what one may assume here is that there is a torsion here, because it was actually two torsion for the generic fiber. And then similarly, so what you get, probably I write it just there. Sorry. Similarly, any smooth quartic, which is defined over Q-bar, which specializes to one of these ones, specializing to y as bar, is not universally CH0 trivial. So it really allows you to produce examples over Q-bar, and even it's more explicit than the previous examples, because you know that what you want to take is something which specializes to some of these examples. Okay, so now could you please open the projector? So this is all I wanted to discuss for quartics, and let me just finish with a couple of comments. Well, we have these three steps, and well, we discussed the invariants that we use. So let me comment on the second and on the third steps. Well, for the second step, so essentially the invariants we used were related to the Brauer group. But also one can use the differential forms. So these were used by Totaro following the construction of Color. Here is very important that the variety Y has mild singularities. So if you have your favorite variety such as Bj, and you want to specialize it to something, then you have to care, if your result is singular, then you have to care that it's not so much singular to have this resolution, which is universally CH0 trivial map. And this is, well, it's not maybe easy to produce such examples. And also in this third step, for really producing a specialization, well, for quartic it was easy. Just let's take a quartic and then we have immediately a family. But in some cases it could be actually tricky. So in particular, so let me go back to the list of examples here. So Claire Voisin, she proved that such a double cover can be specialized to Artin-Mumford double cover which has 10 nodes. So this more or less tells you that the nodes can be smoothed independently, but it's an argument. And also for conics, well, actually, if you want to produce a family staying and working with schemes, then it could not work. What they did is they used some stacks constructions to produce a specialization. Okay, so let me go back to comments. Okay, so if you still want to produce some more examples, well, there are some other examples of varieties Y with higher dimensional non-trivial normified cohomologies. So for I at least 3, so they were produced by Colliot-Thélène and the younger ran for I equals to 3, and then by Asok for higher i's. But now the coefficients of this Y are quite complicated, they're quite unbalanced. So the question would be, what can be specialized on it? So how can one run the step 3? So I said everything I wanted to say. Thank you for your attention.
Questions, please, comments? Perhaps you said this already, but I didn't quite catch it. Which one of those quartics are unirational?
Okay, so the question was, I guess that you don't have a microphone. The question was, which of these quartics are not unirational, right? So there are some particular quartics. Well, I can probably write an equations, and that you can probably find it in the original article by Skovsky and Manin, where by some geometric method they prove that they are unirational. Like you have some particular surface, then you have some tangent space, etc. But in fact, well, that's I found that's more or less the same. The only method to prove that they're unirational, and I actually don't know. So we were not thinking if this particular unirational quartic is stably rational or not. It does this fit in this? But if you give me a quartic, there is this argument for over Q bar, which tells you which precise quartic is not like retract rational. But if you give me one, I probably I won't be able to say if it fits in this method or not. Okay. And for unirational, so there are some precise equations, but well, that's it.